Dr. Seema Jalan is Professor and Head Department of Geography in Mohanlal Sukhodia University, Udaipur. She is also Director, Population Research Center, Convener, Committee of Courses of Geography. She is also a member, Academic Council and Board of Management of the University. She passed in her MSc in Geography as gold medalist in 1998, PhD degree in the field of electoral geography from University of Rajasthan, Udaipur itself in 2007, and PG diploma in remote sensing and GIS from Indian Institute of Remote Sensing, Dehradun, 2009. She has completed postdoctoral research as UGC Research Awardee from 2010 to 2012 at University of Rajasthan, where she has the 22 years of teaching experience, 13 years of college education, then government of Rajasthan, and 9 years at MLSU since 2013. Expertise in various images of processing she's having, GIS and statistical softwares. Research interests include electoral geography, application of geospatial technology, and applied geographical research, particularly social GIS and urban environmental studies. She completed 3 major research projects funded by UGC, ICSSR, MHRD, and 2 major research projects funded by MHRD relating to development of G-governance G-governance application and web-based information systems are still going on. Presently, she is also establishing Geospatial Center for Skill Development and Entrepreneurship Cell in the Department of Geography, Mohanlal Sukhodia University, as coordinator, with an outlay of approximately 1.4 crores funded by Rashtriya Uchchatar Shiksha Abhiyan, RUSA, MHRD, Government of India. She has authored 2 books and published about 35 research papers in national and international journals. She is actively associated with Department of Science and Technology, Government of India, New Delhi, as member of national level committees and coordinator of academic events in the field of geospatial technology. She organized 2-level 121 days national level winter schools in geospatial technologies in the year 2016 and 2019 under the aegis of DST, Government of India, New Delhi. The third will be held in June 2022. She has been awarded certificates of Distinguished Geospatial Educator by Center of Applied Geometrics, CEPT, University, Ahmedabad in 2019. So, very interesting introduction. We are so much impressed by your presence, ma'am, and thank you very much for accepting our invitation to join us as an expert in this 6 days training program on GIS. So all the participants, please join me in welcoming our eminent lecturer of the first session of 2nd day of this training program. Welcome, ma'am, and please take the charge of the session.
Thank you so much, Dr. Aradhna. And it's indeed a pleasure and a privilege for me to be a part of this program. And I'm really happy to know that all of the participants are professionals. So I think this is an opportunity that we can actually, because disseminating this technology to the stakeholders is actually a passion and a mission also. So I think I'll be able to convey something meaningful to the participants today. Thank you so much for an elaborate introduction. Today I'll be talking about, I just heard that most of you are engineers, civil engineers and architects. And it's really, I must say that it's a very good decision to learn GIS, Geographical Information System. You must have had some basic introduction yesterday. And today I'll be talking about georeferencing and projections. I'll share my slide first and then proceed. Okay. Is it visible?
Yes, ma'am.
Yes, ma'am.
So, as I said, we'll be talking about projections and georeferencing today. Now, what are projections and what is georeferencing? For the next 3 years, we'll be together, and during this time, we'll just find answers to some questions. Like, why do we need georeference data in GIS? क्या ज़रूरत होती है georeference data की GIS में? Why do we actually need to do this georeferencing? How do we define the location of features on Earth? How do we model Earth? What do these terms mean? We'll be using the terms spheroid, datum, projection, geographical coordinate system, projected coordinate system. What is the meaning of all these terms? What is meant by spatial referencing system or coordinate referencing system? I understand even in your yesterday's hands-on, you must have come across these terms. What is UTM coordinate system, especially because this is the most commonly used coordinate system these days. What is georeferencing? What is a ground control point transformation, resampling, and how to actually georeference in quantum GIS. So the first thing is, why do we need georeference data in GIS? As you all must have been told yesterday. Aradhana ji, is it fine if I continue in English or I should go bilingual?
Ma'am, it's a good, no problem. But I think that will be better if a mixed medium is used.
Okay, yeah. So the thing is,
but we can, okay, but we can hear from other participants also. Is it okay if we proceed with in mixed?
I think I'll proceed in
Yes.
I'll proceed in both the languages. Right. So जैसे कल आप लोगों ने you must have learned yesterday कि basic principle क्या है GIS का? Basic principle है कि हम different types of information को different layers में segregate करते हैं, and all those layers are ओवरले. तो बेसिकली डेटा को लेयर्स के रूप में ऑर्गेनाइज करते हैं. एक लेयर में एक ही तरह का डेटा हो सकता है. शायद आप लोगों ने अभी तक ये पढ़ लिया होगा कि इट कैन बी रिप्रेजेंटेड ब्रॉडली इन for 3 different forms, point, line and polygon. और एक लेयर में या तो पॉइंट हो सकता है, या लाइन हो सकती है, या पॉलीगन हो सकता है. So for different types of information which pertains to a common area and different types of features in form of these basic entities, point, line and polygon, we organize them into layers. अब ये जो layers हैं, कैसे ये जानेगा GIS कि ये जो different layers हैं, ये different features हैं, जैसे आप इस में देख पा रहे होंगे इस डायग्राम में कि अगर मान लो कि डिजिटल फोटोग्राफ है या फिर सैटेलाइट डेटा है तो इट विल बी अ रास्टर. अगर स्ट्रीट्स हैं तो वो एक लाइन डेटा होगा. अगर हाइड्रोग्राफी है तो भी वो लाइन डेटा होगा. पार्सल्स होंगे तो पॉलीगन्स होंगे. बिल्डिंग्स होंगी तो पॉलीगन्स होंगे. zones होंगे तो polygons होंगे. utilities may be line, it may be a point, it may be a polygon. Administrative boundaries will be polygons. तो different type of layers होंगी. अब कैसे ये जानेगा GIS कि ये सारे जो different features आप represent कर रहे हो ये सब एक ही जगह के हैं. They pertain to the same area. So basically organizing principle क्या है इसमें? हम अगर लोकेशन की इंफॉर्मेशन डिफाइन कर दें कि अर्थ पे उन सब फीचर्स की लोकेशन क्या है, उसका एक्सटेंट क्या है, अगर ये हमने डिफाइन कर दिया तो ऑटोमेटिकली ऑल द लेयर्स विल ओवरले, एक दूसरे के एक ऊपर ऑर्गेनाइज हो जाएंगी. सो ज्योग्राफिक लोकेशन इज द ऑर्गेनाइजिंग प्रिंसिपल. इसलिए जो भी हमारा थीम हो, जो भी हमारी लेयर हो, उसमें 4 प्रॉपर्टीज सबसे ज्यादा इंपॉर्टेंट हो जाती हैं. पहला प्रोजेक्शन, ये हम देखेंगे कैसे क्या होता है प्रोजेक्शन. देन द स्केल, जो इंफॉर्मेशन है वो सभी एक ही स्केल पे होनी चाहिए. वो कितनी एक्यूरेटली रिकॉर्ड की गई है, उसकी पोजिशनल एक्यूरेसी क्या है, और इसके अलावा उस इंफॉर्मेशन को किस रेजोल्यूशन पे रिकॉर्ड किया गया है. जैसे इसका एक बहुत ही सिंपल सा एग्जांपल ये हो सकता है कि कोई एक मैप है जिससे आपने कोई इंफॉर्मेशन ली है, वो मैप 1:2000 पे बना हुआ है, और एक दूसरा मैप है जिससे आपने एक दूसरी इंफॉर्मेशन ली है, वो 1:50,000 पे बना हुआ है। तो अगर वो इंफॉर्मेशन का
Excuse me, ma'am.
सोर्स डिफरेंट रेजोल्यूशन, यस
Ma'am, actually, sorry to bother you. Actually, I'm from Tamil Nadu. I don't understand when you talk in Hindi, ma'am.
Okay, I'm fine. I'll just
Yeah.
continue in English then.
Yeah. Thank you
Okay.
so much. Sorry. Yeah.
So there is a different map which has been a different information which has been actually extracted from a map with a smaller scale. Okay, so if we try to integrate both these informations, it might not be very useful. It might not give you that much of insight. So resolution and scale also matters, but today we'll stick to the projection. So now I come to the basic question. We said location is the organizing principle. Then how to define the location of features on the earth? Yeah, you will say, oh, that is very simple. We define the location of a feature in terms of coordinates. That means you can say what is a coordinate? It is a set of numerical values. You all know that if I say that what is the location of Indore, what is the location of Indore? So you will say, okay, this is this latitude and this longitude. It is as simple as that. Now I'll say that if I give you a map, which is a flat, you can say a two-dimensional space, then you can fix the location of a feature with a set of two numerical values, which is the latitude and the longitude. If you say that, I say that no, I want the location information in 3 dimensions, then you add one more dimension, that is the elevation or the altitude. So if we want to fix the location in 2 dimensions, we need a set of coordinates having 2 numerical values, latitude and longitude. If I want to fix in the 3D space, then I want 3 numerical values, which is the latitude, longitude, and the elevation. So first we'll talk about, and I am very sure most of you must be knowing all these concepts, but maybe you'll get I'll be able to make you think some more. If you say latitude and if you say longitude, then what exactly does latitude mean and what exactly does longitude mean? If I say that, say 30 degree latitude, then what do I mean by 30 degrees? What is this 30 degrees? This 30 degree is the angular distance, okay, measured in degrees, minutes, and seconds. Angular distance of what? Of a point. So I can say that I have a point somewhere here, which I call 30 degree north latitude. This is being measured in degrees, minutes, and seconds. There are other ways of defining this also, degree, decimal, degree. It may be defined in meters also, but right now we're talking about angular distance. So we'll say degree, minutes, and seconds. This point may lie north or south of the equator. And all the lines which have the same latitude are called as parallels. Okay, so we must understand the latitude is just a point, and there may be several points which may have the same latitudinal value, and if we join them by I may say a hypothetical line, then imaginary line, you call it a parallel. Similarly, the longitude is again the angular distance, but this angular distance is being measured again in degrees, minutes, and seconds. It is being measured east or west of the prime meridian, which is most commonly, not essentially, it passes through Greenwich in London, and for most of the purposes, we consider it as the prime meridian. Again, all the points, if joined by an imaginary line having the same longitudinal value, we call them a meridian. Okay, so if I want to fix the position of some point on Earth, then I need these two values, latitude and longitude. But we must remember that when I talk about latitude and longitude, I am talking about the position of a point on a spherical Earth, not in a two-dimensional space. Okay. So then the question comes, are latitude and longitude enough to fix the position? Okay, if I say that, if you tell me that, I ask you, where do you live? And you say that, ma'am, I live in flat number 503. Can I reach your place? If I want to come over to your home, can I come? No. So I will say that latitude and longitude are just the flat number or the house number, but I don't know the colony, I don't know about the city, I don't know about the state, I have no other information. So just with the latitude and longitude, I cannot reach your place. Coordinates in themselves are like house number without an address. I will tell you why. You are saying that latitude and longitude is the angular distance which is measured on the earth. My question is, what is this earth? What is the shape of this earth? What is the size of this earth? What are the dimensions of this earth? Where is the center? Where is the reference point where you want to measure, where you are measuring this angular distance? If I tell you go 5 kilometers, you will ask me, ma'am, 5 kilometers from where? From my office or my residence? Okay, so it is just like that. If I say that latitude and longitude is the angular distance which is measured on the earth, then I have two questions. What are the dimensions of this earth, and where is the center of this earth? Where is the reference point where you are measuring this angular distance? So we need to define the earth. We need to model the earth mathematically on which the position has been fixed. So I ask, what is the shape and size of the earth? To define the shape and size of the earth, I have to define the spheroid, the ellipsoid, and the geoid. These terms, spheroid and ellipsoid, for all good purposes, they are synonymous, and geoid defines the vertical undulations of the earth. So we actually, spheroid and ellipsoid will define the shape and size of the earth, and geoid will define the surface undulations. You can say it will give you the reference surface for measuring the third dimension. Okay. Then where is the center at which the coordinates are being measured? That means where is the origin, which is the reference point for measurement. Datum will define that. Where with the point? Okay, now you know about the shape and size of the earth, you know about the origin. Then again, there is one more question. Where will the point lie if fixed on the flat surface? Right, till now we are talking about a spherical earth. But I need to fix the location on a two-dimensional surface, on a flat surface, on a map. Then how to convert this spherical earth into a flat surface in a map, in form of a map? That will here where projection comes in. Okay, so this defining the position, to fix the position, is not a small journey. It is a long journey where you need to pass through all these phases. Okay, so we use a series of concepts and techniques that progressively transform measurements carried out on the irregular surface of the earth to a flat surface of a map. Actually, the earth is like this. कहीं पे high है, कहीं पे low है. It has an undulating irregular surface. But to make the measurements, I have to simplify this. And progressively, using a series of concepts and techniques, I simplify this concept and I convert it into a flat surface of a map. This is what I actually need in GIS, because in GIS, what I have layers, and in those layers, I have to show all the features in form of a two-dimensional layer. Features which are there in a two-dimensional layer. That means a flat surface. So I convert this into this. And during this course, during this journey, I pass through the concept of geoid and ellipsoid. I pass through the concept of datum. I pass through the concept of map projection. And then I am able to reach from here to here. So now we'll understand how do we model the earth. The first thing is the earth is huge. in order to handle that, first what I do is I assume that I use a reduced earth, a smaller earth. Okay, so what I do is you can say that like you all have seen a globe, so you can say that I assume that we have reduced the size of the earth as per some scale in some proportion, and that smaller uh, you may say that smaller form of the earth is, you can say it may be considered as a globe, or I will call it a reduced earth. Okay, so this proportion in which it has been reduced, it is known as the map scale. Okay, so the scale is the distance on the globe divided by the distance between the same 2 points on the actual earth. Okay, now again, to prepare the map, I need to convert this 3D reduced earth into a flat surface. That is done by the map projection. Again, when I convert this spherical reduced earth into a flat surface of a map, again some scale distortion creeps in. Okay, that is known as scale factor. That means the distance between any 2 points on this reduced earth and the distance between the same 2 points on this flat map, they will not have a one-to-one relationship, but there will be some kind of change. That ratio is known as scale factor. So the scale factor is the ratio between the distance between any 2 points on the flat map divided by the distance between same 2 points on the globe. Okay, so this is the globe. We have a concept of scale and we have a concept of scale factor. So the thing is, now here there is one more thing that we need to remember, that most of the times we consider Earth as a sphere, but actually Earth is not a sphere. Earth is a spheroid. It is slightly larger in radius along the equator than the radius along the poles. So it is a bit flattened at the poles and therefore it is a spheroid. So I am not modeling a spherical earth, but I am modeling a spheroidal earth. So let's see how to define an ellipsoid and a spheroid. As I said, a closer approximation of the physical shape of the real earth than a sphere is an ellipsoid or a spheroid. This concept of ellipsoid and spheroid accounts for the variable radii. We said that the radii is not the same along the equator and along the poles. That means this concept of ellipsoid or spheroids, it takes into account this reality that the radii is different along the equator and along the poles. And the earth is slightly flattened at the poles. That concept is known as spheroid or ellipsoid. So you can just imagine as if you have some kind of an ellipse which you just turn it around and it will rotate, and then whatever shape, solid shape you will obtain by rotating that ellipse on its minor axis, the smaller axis, the polar axis, then that will form a spheroid or an ellipsoid. There are many definitions of spheroid. If I want to actually define this spheroid, what I need two main measurements. No, this A, that means the equatorial radius, and B, that is the polar radii. So there may be different measurements of these two, A and B, and therefore several different definitions of spheroids are in vogue. They are being used across different countries. We'll not go much into that, but we'll just understand that there are many different definitions of spheroid which are being used by different mapping agencies across the world. Now this, as you can see, now what we have done, we have simplified a bit. This was the actual surface of the earth, very irregular, very undulating. Then we have simplified that surface into a regular ellipsoid. You can see this white colored ellipse. This is a ellipsoid. So what you are doing through this concept, you are simplifying this irregular surface into this smooth ellipsoidal surface. This will define the shape as well as the size of the Earth. So in the definition of a spheroid, this we have done here. You can see here. If you say that I'm using a particular spheroid, I'm defining the Earth using a particular spheroid, what all you will have to define? You will have to define the semi-major axis, you will have to define the semi-minor axis, and then we give one more parameter, that is the flattening. Flattening is represented by small f, and that is actually nothing, the difference between these two radii and divided by the major axis, a minus b upon a. This gives you the difference between the two axes of the spheroid. That means how flattened your spheroid is. Now, once you have defined the spheroid, still the problem is not totally solved, because the thing is where to pin this spheroid. Okay, there is, you have the actual Earth, there is a center of mass of the Earth, which is considered as the origin of the Earth, and now you have actually defined that Earth in form of a ellipsoid. You said, okay, this ellipsoid has this much of A and this much is B, and that is the flattening. Now the thing is, you have to fix this ellipsoid on the actual Earth. And when you fix this, then does the center of your ellipsoid coincide with the actual center of mass of the Earth? That is the another question. So by definition, a datum is a model that describes the position, direction, and scale relationship of your reference surface for positions of on the surface of the Earth. Now you need another concept, that is the concept of a datum. This datum will tell you that where is the origin of your ellipsoid in relation to the surface of the Earth by an anchor point. If you fix your ellipsoid on the actual Earth, then will these two centers coincide, and where will your ellipsoid coincide with the surface of actual Earth on the surface? Where will it coincide at the surface, and will it coincide at the center of the Earth? These are the questions before me, which will be answered by the definition of the datum. So definition of a datum consists of an origin, positioning of the ellipsoid in relation to the surface of the Earth by an anchor point. Okay, so my datum will tell me where my ellipsoid is coinciding with the actual surface of the Earth. Then the parameters of the spheroid, of course, are inherent in this definition. And what is the separation of the spheroid and the Earth at the origin? So what I said there are many different definitions of the spheroid. Of a spheroid, you know. So where do these definitions vary? There are some ellipsoids which are fixing very well with the actual Earth. There are some which may be fixing better for a particular country. As we have for India, we had Everest. So Everest spheroid was fixing very well for Indian region. But there may be some others which, if this is a particular ellipsoid, it may be good for India. It may not be good for the Americas or Europe or any other part of the world. So there are different datums. Those datums which have a good fit for a particular region on the Earth are known as local datums. So we have many different definitions for local datums. There are some others which will fit well with the whole Earth, okay, fairly well with the entire Earth, and whose center is coinciding with the center of the mass of the Earth. These are known as global datums. As you must have you must have come across WGS 84. WGS 84 is a global datum which is fitting fairly well across the globe, and the center of the ellipsoid is coinciding with the center of mass of the Earth. Okay, and therefore, for this reason, this datum is being used across the world for GPS systems. Okay, you must be using GPS in your mobiles, and all these GPS measurements, they are being made on this datum. That means this definition of the spheroid, where this semi-major axis, you'll get it in any standard book or text on GIS. Or this is the flattening factor, and this is the datum which is being used for all the measurements being made by the GPS system. Okay, so now we understand, we have defined the shape and size of the Earth. We have seen how well does a spheroid fit with the actual Earth, whether it is a local fit or it is a global fit. Okay, now we come to, when we have defined the Earth, we come to the measurement. We come to the fixing of the position of a particular point. So position of a point on the spherical surface of the Earth. As we said, we need two angles. We need those. Which are these two angles? These are the latitude and the longitude. These angles, where are these being measured? These are being measured on two orthogonal planes, equatorial plane and zero meridian. These two planes intersect at the center of the Earth. This is the equatorial plane, as you can see. This is the equatorial plane, and this is the, I'm sorry, this is the equatorial plane, and this is the meridional plane. Okay, and both these planes are intersecting where? These are inside the Earth, they are intersecting at the center of the Earth. And here on the surface of the Earth, you can say that you have the intersection where with both these planes are cutting across on the surface also. So you can say the prime meridian and the equator serve as the baselines of the geographical coordinate system. When you make any measurement on this spherical Earth, what you will do? You will just see what is the angular distance from this reference point. And this angular distance, if you say it is 30 degrees will be measured where? At this center, inside the Earth. So which is the actually the you can say which is the arc. This arc is being formed here at the origin of the Earth. Okay, so the longitude values, if you consider this line of measurement, then if you move this way, you will be measuring longitudes, and if you move this way, you will be measuring latitudes. So in simple way, I can say the X values are the longitudes and the Y values are the latitudes. So now do not confuse the geographical coordinate system with datum. Datum is only a part of the geographical coordinate system. Datum defined, GCS is a unit of measurement. You are measuring the latitude and longitude in degree, minutes and seconds. Plus you have defined a prime meridian, which may be the Greenwich meridian, which may not be the Greenwich meridian. Whichever prime meridian is there, the intersection between the equator and the prime meridian will define the reference point on the surface of the Earth from where you will draw the arc to the point for which the location will be fixed. And then you have defined a datum based on a spheroid. All these together will form the geographical coordinate system. So for most, as I said, for most the GCS meridian, prime meridian is the Greenwich line. Now let's understand here. If I say geographical coordinate system, I say that let's say a particular place has 30 degree north and 30 degree south values of latitude and longitude, north and 30 degree east, 30 degree north and 30 degree east coordinates. Then now you should understand that this 30 degree north and 30 degree east is not just a simple numerical value, but this includes definition of the spheroid, definition of the datum, definition of the prime meridian, plus whatever origin of the reference system has evolved out of these three definitions, then it is a measurement from that intersection or that point of reference. This will define these geographical coordinates. As I said, the angular distance can be measured is in degree minute seconds. You all know that. It can also be expressed in form of decimal degree, जिसको हम DD बोलते हैं. DD is very simple. You just convert the minutes and the seconds into degrees. So if I say that there is some, I say that 30 degree, 30 minutes and 0 seconds. Okay, so we all know that 1 degree has 60 minutes and 1 minute has 60 seconds. So what you can say? You can say either you can say 30 minutes and 30 degree and 30 minutes, or you can say 30 degree, 30.5 degrees. That is the same thing. So 30.5 degrees, where you have converted the minutes and the seconds also into a degree. That is the expression in form of decimal degrees. And where you say that it's degree, minutes and seconds, then it is you are giving the actual values of degrees separately, minutes separately, and seconds separately. So these are two major ways in which we express these coordinates. Now what we did, we defined the shape and size of the Earth. We have defined the origin of the Earth, whether it is fixing well with the Earth, actual Earth or not. We have also defined a reference point from where we are making the measurements, the angular measurements. Okay, fine. But my problem is still not solved. Because what I need is in GIS, I need 2D layers. Now there's one more problem, that I have to convert this 2D, 3D surface into a flat surface. Here I make use of the projections. Okay. So most of the GIS layers are 2D. Method by which we transform the Earth's spheroid, that is the real world, to a flat surface is known as projection. We can do it either on paper, that we used to do traditionally, and now with all GIS softwares at our disposal, we do that digitally. Okay, so what projections are doing? Projections are actually transforming the coordinates from the geographical coordinate system to a planar coordinate system. We were defining the location, we were fixing the location on a 3D Earth. Now we try to fix that position on a flat surface. For that, we are making use of the projections. So you have angular measurements. Using a map projection, you convert it into planar measurements. Okay, so a curved spherical Earth is being projected into a flat map. It is as simple as that. You just imagine that you are holding a mesh, okay, any simple mesh that you may have, and you put a light on one side and you put a flat surface on the other side of that mesh. Okay, so what you'll actually see here, like you can at times you see your shadow on the wall. So you have a mesh. This is the graticule. These are the parallels and the meridians on the reduced Earth. And when you put the light here, all these wires, you can say, they get projected on whatever surface you are holding. We call it a developable surface. If you call, what is the technical term for it? It is the developable surface. Okay, the planar surface. So what you will be seeing, you are seeing here, you are seeing the shadows of all these lines of the graticule. And you just trace them and you will get the projection. Okay, so it is that simple concept. Therefore, we call it a projection. You have projected this graticule on this planar flat surface. Okay. Now these map projections may be they may be put in 3 broad categories. I request the participants to please mute themselves. All of you, please check. If you are unmuted, please mute yourself. Okay. Now, what you do, you just you have three main families of map projections. You have cylindrical projections, you have conical projections, and you have zenithal projections. Okay, as you can see, there's a difference. This is the developable surface, what I've told you. If this developable surface, if this developable surface is in form of a cylinder, you call it a cylindrical projection. If this surface is in form of a cone, you call it a conical projection. If this surface is just a flat surface, a plane surface, then you call it an azimuthal projection. Okay. What we do is, then you can you see the bulb inside? So we have a source of light. Okay. Now we have different projections also based on where is the source of light placed. That source of light may be inside this mesh, this graticule, inside the graticule of your spherical earth. Okay. Inside the globe, you can say, a see-through globe. This may be at either end. It may be placed here, or it may be placed here, or it may be at a distance. If this source of light is inside the globe, it is known as a mnemonic projection. If it is at either end, at diametrically opposite end, it is known as a stereographic projection. If it is somewhat distant from this, it is known as an orthographic projection. Okay. So first criteria of classifying whether the what is the shape of the developable surface, whether it is cylindrical, conical, or azimuthal, or where is the second criteria, where is the source of light? It may be mnemonic, stereographic, or orthographic. These are the main families of map projections. So we come to the conical map projections. These conical map projections, they project the globe onto a cone. It is like we wear our birthday caps. The same way you put this cap on the globe, and when you put this cap on the globe, then it will touch the globe at some parallel. Okay. In the simplest case, globe touches the cone along a single line parallel, and it is, we can say, tangent on that parallel, and that parallel is known as standard parallel. This cone can be secant also. As you can see, it is not always tangent, but it can be secant also. That is an imaginary situation where you think that your cone is passing through the globe. Okay. So it can be secant too. Other latitude lines are projected onto the cone. Then you place the source of light, and then these reticule will get projected on this cone. You trace all those lines, and then you cut the cone across along this line. Okay. When you cut it along this line, then you will get a shape somewhat like this. Here, these concentric lines are your parallels, and these spokes are the meridians. Okay. So this, and the meridian which is opposite to this line along which you are cutting is your central meridian, which will lie in the center. So this will be a cylindrical projection where you will project this globe onto a flat surface. Then we come to the azimuthal map projections. In azimuthal projections, you just project the globe onto a flat surface. The simplest form is again a surface which is tangent at any one point on the globe. Any point of contact may be used, but mostly you put this surface tangent to the poles. And in such case, we call it a zenithal projection. When another location is used, it is generally to make the map of small area. I want to make the map of this region on the globe. So I will put this surface tangent here. Okay. But most of the cases, it is put tangent to the poles. When the poles are used, longitude lines will look like hub and spokes. Again, your parallels will be concentric circles and the meridians will be like spokes. Okay. So depending on where you are putting this surface, you can have three types of projections. Polar, which is the most common case, where your surface is tangent on either of the poles, and you get a projection somewhat like this with concentric parallels and like the meridians like the spokes. And this is a mnemonic case where the source of light is in the center, inside the globe. Then you can also put this flat surface along the equator. It may be tangent on the equator. You call it an equatorial case. And you can also put it along any other parallel. That will be known as an oblique case. Okay, so we can put the surface like this: polar case, equatorial case, or oblique case. Then the source of light can be at the center. You call it a mnemonic case. It may be diametrically opposite to the surface along that particular pole, along the other pole. This will be known as stereographic case, and it may be at a distance so that all the rays of light are parallel. We call it orthographic. Okay. Coming to the cylindrical map projections. Now this is another case where a developable surface is in form of a cylinder. It is like you take a ball and you put just fold a paper, seal it at the edge, and you put it through that ball. That is a cylindrical map projection. Creating by wrapping a cylinder around the globe and in theory projecting light out of that globe. The meridians are equally spaced and perpendicular along to the parallels. Projection in such case, what are we getting? We are getting these perpendicular parallels and meridians. In a cylindrical projection, always your parallels will be horizontal parallel lines, and your meridians will be, again, they will be parallel to each other and they will be perpendicular to the parallels. Spacing between these parallel lines will vary depending on whether it is a mnemonic case or it is a stereographic case or it is an orthographic case, and whether it is a normal or a transverse or an oblique case. In cylindrical projection, you always need to remember that your meridians will never converge along the poles. But you know that meridians converge at the poles. So as you can see, the high amount of distortion it is having, that the pole is equal in length to the equator. So you must also understand that when we try to convert the globe into a flat surface, then there are many types of distortions that they come in. Okay, there may be a distortion in the shape, there may be a distortion in the area, and there may be a distortion in the distance, there may be a distortion in the direction. If there is, as you can see Greenland here. Okay, I say, what is the distance between the two edges or the two coasts of this island? Okay, then there must be some distance. But if you see the same here, can you see this here on this on the globe? And you can see the same here on the cylindrical projection. It is multiple times larger than that. So there is a distance in the area, there is a distortion in the area, there's a distortion in the shape, there's a distortion in the distance, there may be a distortion in the direction also. So several types of distortions creep in. Okay, then whereas I just said that there is one parallel which is known as a standard parallel. Which is that parallel? It is that parallel along which the whatever surface you are using, that surface is tangent to the globe. This parallel is known as standard parallel. This parallel will be standard parallel. Now, can we say what is a standard parallel? Of course, where a surface is touching the globe, the scale is not getting distorted. Okay, so what is standard parallel? Standard parallel is that parallel where the scale distortion is nil. That means, in other words, you can say standard parallel is true to scale. The scale is true, undistorted along the standard parallel. Okay, so this is one parallel where you can find that there is no distortion in the shape, area, distance, or direction, but along only that parallel. The process of flattening induces varying scale changes in the east-west and the north-south direction along the parallels and meridians. This causes distortions in one or more of the spatial properties. This may be shape, area, distance, and direction. Then what to do? Are the projections useless? Then why are we studying the projections? Projections are not useless. We have certain projections, they conserve some properties. And there may be distortion in some properties out of these four, and there may be some properties may be conserved. Okay, so these scale changes in the east-west and the north-south direction are not random, but these changes are systematic. And we can, in different types of projections, it is possible that we can either conserve the shape or the area or the distance or the direction. In this, shape and area can never be conserved together. Either one of them will certainly be distorted, but the other properties can be conserved together. Okay, so now, if two properties are to be preserved, then one is always direction. So it is possible that we can preserve direction along with the shape or the area. Those projections where you can preserve the shape are known as conformal map projections. Those projections where you can preserve the area are known as equal area or homolographic map projections. Those projections where you are able to preserve the distance, that means if you measure the distance between any 2 points on a map which has been prepared on that projection, then the distance will be the same which is on actual Earth. That is you say that is an equidistant map projection. And then there is another projection where you can preserve the direction. Like if you want to prepare a map for navigation, then direction is most important. Then those are known as Azimuthal Map Projections. So what we understand when we actually conserve, we say that the area is distorted. Okay, see. This is a Mercator projection. For example, you can see if I prepare the map of the Americas and Greenland on a Mercator projection, the Greenland will appear somewhat like this. And if I measure the area, it will come out to be 8,27,000 square miles. If on this projection I measure the area of South America, it will come out to be 6.8 million. I'm sorry. This will be smaller than Greenland, but the actual area of Greenland is 8,27,000 square miles, and the actual area of South America is 6.8 million square miles. So this is the actual sea. This is the actual size of Greenland. And this is the actual size of South America. And when you prepare this map on Mercator projection, the South America becomes smaller than Greenland. So this is known as area distortion. Okay. Distance distortion. In one projection, the distance between both these coasts of North America is 4,300 kilometers. In another, it becomes 5,400 kilometers. So you need to think that whenever you are using a map prepared on a particular projection, you must know what are the types of distortions which are there. Then we come to the shape distortion. Okay, I say that no, Mercator projection is actually inflating the area. So I will go for a projection in which the area is conserved. So this projection is giving you the actual area, but then the shape is totally distorted. So you have to choose. There's a trade-off between the what properties you want to conserve. Okay. So what we did, we have modeled the Earth. We have defined its shape and size. We have seen its fit by defining a datum. We have defined a point of origin. Then we made the measurements on a spherical Earth using a geographical coordinate system, and we converted the spherical Earth to a flat surface using a projection. Now my problem was I want to fix the location of a particular point on the Earth. For this, the final concept that I need is the spatial referencing system. Map projections and coordinate systems serve two different purposes in georeferencing. What are these purposes? The function of map projections, as we talked, is to define how to convert the curved surface onto a flat map surface. Then, once you have converted the curved surface onto a flat map surface, what you need to do is you need to have some kind of a coordinate system on which you can make the measurements. You must have a 0, 0 from which you will measure the longitudes east or west to it, and you will measure the latitudes north or south of it. That is known as a coordinate system. So what we do is we superimpose the coordinate system onto the referencing framework which is given to us by the projection, and by which the positions are actually measured and computed. Okay, so this is the CRS or the SRS which you actually come across when you are working in GIS. So let's summarize what is a GCS, what is a projection, and what is a PCS, a projected coordinate system. GCS tells me where on the Earth my location will draw. If I have a point on the surface of the Earth, geographical coordinate system will tell me where is that point on a spherical actual Earth. Then projection tells me how to draw this spherical Earth on a flat surface. And the coordinate systems tells me that within this framework which has been given to me by the projection, how do I measure the location? Okay, where will the point actually lie? Where is the 0, 0? Where is the origin from which that measurement is to be made? So these are three concepts which we used in the coordinate definition during when we are working in GIS. So coordinate systems are constructed based on the map projections. They are not map projections themselves, that you have to understand. So here I will tell you that, like, if the flat number 503 is in X society, it is in at a different place. If flat number 503 in a Y society, it will be at a different place. If the same flat number 503 is in the Z society, it will be on a different place. So you must always remember that the same coordinates, 30° north and 30° east, that particular coordinate location will map or at different places, in different projections, in different datums, on different spheroid or ellipsoid. So you must always remember that whenever I talk about a particular coordinate set of coordinates, it is very, very essential that I say that the flat number 503 is in X society, on this road, in this city, in this state, and in this country. Okay, that will be a complete address. So the coordinate system implies a particular projection, a particular datum, a particular spheroid and ellipsoid. Now I come to the very important projection, which is known as UTM projection, Universal Transverse Mercator projection. This is the projection which is now being used by all the mapping agencies across the world. If you know that in India also we are all the topo sheets have been drawn afresh, which is known as the open series map under the national map policy, new national map policy, and these topo sheets have now been drawn on UTM projection. Okay, so this is an important projection, so I will discuss this a bit. UTM is based on the transverse Mercator projection. So it is basically a Mercator projection, which is a cylindrical projection, and it is the transverse case of Mercator projection. What do we mean by transverse case? That it is not, this cylinder is not tangent along the equator, but this cylinder is tangent along the poles. So it is the transverse case of a cylindrical projection, cylindrical Mercator projection. It is a conformal projection. When I say conformal, what do I mean? I mean that the shape is being conserved. The distance, all distances, direction, shapes and areas are reasonably accurate close to the central meridian. It is drawn in such a way, Mercator, transverse Mercator projection is drawn in such a way that along this central meridian, along the central meridians, all distances, directions, shapes and areas are reasonably accurate. Not exactly accurate, but reasonably accurate. That means all the four properties are reasonably accurate along the central meridian. Shapes and angles within any small area are essentially true. So all my purposes can be solved in the area which is near to the central meridian. So the UTM coordinate system, this has been, we can say that it is a modified cylindrical Mercator projection. इसमें क्या किया हमने? What we did was, instead of putting one cylinder, we have put 60 different cylinders, okay, at every 6-degree meridian. Okay, at an interval of 6 degrees, I have put one cylinder, then I rotate it a bit and I make it tangent to another meridian which is 6 degrees off. Then a third cylinder, again 6 degrees off, then a fourth cylinder, again 6 degrees off. At every 6 degrees, I have a central meridian. Okay, and as you can see here, so in this region along the central meridian, all four properties are reasonably accurate. The scale is more or less conserved, and all the four properties together are reasonably accurate. So what we got? Actually, what I did, I have cut this whole cylindrical projection. I have cut out this strip of 6 degrees. Then I have joined all these strips, 6 degrees. So how many strips do I have? 60 strips. Okay, and you we are able to map only up to 84 degree north and 80 degrees south. So we have 60 zones, each of which is covering 6 degrees of longitude. So the first strip, second, third, fourth, and the first starts from a 180 degree west. So you start from 180 degree west, then from 180 degree west, then 6 degrees, 6 degrees, 6 degrees, and every zone has the central meridian. So it is 3 degrees off here and 3 degrees to the west. Okay. Then you have the parallels. So you can say that you get this grid. Okay. This is 6 degrees in the east-west direction, and it is 8 degrees in the north-south direction. So you get this UTM grid, and India as well as Indore lies in 43° north, 43 number, this 43 number zone. We have numbered all these zones starting from 180° west. So 1 to 60 zones we have. India, and particularly western part of India, Udaipur as well as Indore, lie in the 43rd zone. Then within this zone, what I'll do, I will define whether it is north to the equator or south to the equator. So I say that we lie in 43 north, UTM grid 43 north. Then these different cells in this grid have also been given some alphabets. So you can just see that the UTM are now how to define the location of a particular, position of a particular point in this projection. Okay, we call them UTM coordinates. Now, this is Earth central meridian. We talk about only one zone right now. This is Earth central meridian. My zone extends 3° to the east of this central meridian, 3° to the west of this central meridian. Okay. This total, you can say the total distance is, the measurements are made in meters on a UTM projection. So this total distance is 10 lakh meters. Okay. So if I say this is 0, this is 5 lakh meters to the east and 5 lakh meters to the west. Then what I do, I say that I don't want negative values. If I say 5 lakh, this, if I keep this as 0, then these are positive values, these are negative values. But I say I don't want to have negative values. I should have all the positive values only. So what I do, I shift this origin here. I put the 0 here. So then my central meridian becomes 5 lakh meters east to the origin. Therefore, I call all these longitudinal measurements as eastings in the UTM coordinate system. Okay, and this falls because this is the false origin from which I am making the measurements. So I call it false easting. Okay, so in a UTM zone, I have longitudinal measurements starting from 0 till 10 lakh meters in form of false eastings. Then similarly for the latitudes, latitudes are extending from 80° south to 84° north. I have an equator. The measurements north of the equator are positive, measurements south of the equator are negative. Again, I don't want to have negative numbers. So what I do, I shift the origin to the southernmost point and I keep my 0 here. Okay, so this is my 0 for the eastings and this is my 0 for the northings. Then I call all these measurements which I will make for the latitudes, I will call them false northings. So your equator is assigned a value of 10 million meters. Okay, so 0, 0 comes here. This is a 6° wide zone. And in this zone, all the 4 properties are reasonably accurate. And you can make you make all positive measurements in form of false eastings and false northings. Okay, so if now I want to define the position, I want to fix the position of a particular location on the Earth in the UTM coordinate system, then what I will do, I will have certain measurements for false easting, some measurement in meters for false northing. Then I need to define, I am talking about which zone, because these eastings and northings are common for all the 60 zones. So I will say that my zone is 43 and then I will say it is north or south of equator. So if I talk about the UTM coordinates of Udaipur, then I will say I lie in 43 north zone, and my false eastings and false northings are whatever values I have in meters. Okay, so that is all about what I have to say about the coordinate system and projections. Now, if there are any questions, you may please ask me. Are there any questions? Any queries?
Okay, the forum is open for discussion. Participants can ask their queries.
Okay, either you have understood everything or you have understood nothing. So,
Actually, it was a
I
wonderful presentation and we learned a lot, ma'am. Thank you.
Thank you so much. But still, we are still together for 1.5 hours. So we'll just break for 10 minutes and I'll be back. Then, meanwhile, you can just think upon it. And if you have any queries, then we can take up the queries first and then proceed for georeferencing. Okay?
Okay, ma'am, thank you. It was a wonderful presentation, and geography made easy for us actually. Like I never thought that just a location, so much of calculations and so much of knowledge is there. But you presented and made everything easy for us now. And I think the participants are also very curious to know, to earn more knowledge in our next sessions also. Like they will be more comfortable now. I think they will be more comfortable using GIS now. Like particularly in selection of data or what type of data they should need for a particular purpose. They'll be more clear now. So any query from participants?
Actually, this is a very, very important concept. When you actually work in GIS, then most of the times you will find that your layers are not overlaying. Or when you acquire the data from any other agency, that you have some data and they have given you some data, and then you put them together in the GIS and then you know, ma'am, they are not overlaying. The main thing you need to understand is that what is the projection of that data? What is the datum? What is the spheroid? You have to bring them onto the same platform. As I said, the same flat number is at different places in different societies. So the same location will map at different places in different projections and the different datums. So that is the fundamental. And I must say, when we work with the students or the scholars, this is 90% query is, ma'am data overlay नहीं हो रहा, ma'am data खुल नहीं रहा, madam इधर उधर जा रहा है. That is because you have to understand the coordinate system. So it is a fundamental concept and you may think on it for 10 minutes. We'll meet again. And I'll just say that if you have any smallest query also, because as I said in my first slide, the first organizing principle in GIS is defining the location, understanding the location. So you can always ask me anything, any smallest query that you have, you can ask me without hesitation. Then we'll proceed for georeferencing, which is basically that how to attach this location information with your data. So before proceeding on that, we need to understand location. So we meet after 10 minutes and then we can first take up queries if there are any, and then we'll proceed. Okay. So
okay, ma'am. Madam, can we have something like a discussion on a actual map? Like all these terms are mentioned there, and can we relate?
We'll do it in georeferencing. We'll be doing it in georeferencing.
Okay, sure, ma'am. Thank you so much.
I'll give some more details there.
Okay. Thanks a lot, ma'am. Thank you.
Thank you.
So we'll all reassemble after 15 minutes. That will be fine, I think. Okay, so we'll have a break of 15 minutes, and after 15 minutes, we'll reassemble sharp at it's 11:30.